Alright, so let's now try doing this. Let's evaluate the integral over c of quantity root 3 plus sine of x plus 4y dx plus quantity 6x minus the fraction 3 plus sine of y squared over tangent inverse of y plus 2, close parentheses, dy, where capital C is the circle x squared plus y squared equals 64 oriented counterclockwise. Okay, now if you want to compute this integral directly, you could. It'd be a lot of work. What you'd do is this, but instead of doing this, instead of parametrizing, which you could do, let's just start outlining some of what you do here. So you'd have x of t is equal to, circle of radius 8, right? So 8 cosine of t, y of t is equal to 8 sine of t. T would go, it's all the way around, so 0 to 2 pi. And dealing with difficult integrands, let's say what we mean here by difficult integrands. So take a look right there. Root 3 plus sine of x? That sounds like a mess. 4y doesn't sound so bad. What about over here? What about that integrand? 6x? That doesn't sound so bad. But after that, there's a minus, and then this fraction. There's a sine of y squared in the numerator. There's an arctangent of y in the denominator. That sounds like a mess. So instead of doing that at all, let's apply Green's theorem. So let's say what we have looks like this, and let's turn it into that. Okay, so if we do that, let's draw a picture of the region D. So it should be, if the circle is, look, maybe we should draw actually first the circle. Yeah, so there's the circle, radius 8. Okay, that's capital C. So then D is the filled in circle. It's called a disk technically when it's filled in. Okay, still radius 8. So there's a picture of D. So then the integral over C of root 3 plus sine of x plus 4y dx plus, what's the next term in the question we were asked? Oh yeah, I gotta copy this down here. 6x minus fraction 3 plus sine of y squared over tangent inverse of y plus 2 dy. Let's just note that following the notation in Green's theorem, that's capital P, and then in the next set of parentheses is capital Q. Then by applying Green's theorem, we'll instead look at a double integral. Double integral over D. We've already drawn that D is the filled-in circle of radius 8, or technically the disk of radius 8. But then what we need here is we need the first term here should be the partial derivative of Q with respect to x. So stare at this, differentiate with respect to x. It's 6. That's it. The second term here, it's all y's and constants, so the derivative there is 0. Then copy the minus sign, that's this minus sign that's there in Green's theorem. And then we need, in this next spot, we need derivative of p with respect to y. So stare at this, there's p, differentiate that with respect to y. The first term differentiates to 0 because there's only x's there. So then 4y differentiates to 4. Okay, dA. So check this out. What we end up with here is equal to, well, the double integral over the region D of just the constant 2, dA, constant function 2. Now, we could start writing this integral, x from negative 8 to 8 and y from negative root, we can do all that. But just like with other double integrals, based on the shape, we should really convert to polar. It's just going to be nicer, right? So just have integral, still copy the 2, dA, instead of being dx dy, is r dr d theta, r goes from, well, it's a filled-in circle of radius 8, so from 0 to 8, and theta goes from 0 to 2 pi. It just makes this integral way, way nicer to compute, because we'll have integral 0 to 2 pi. 2r is integrated with respect to r, so I'll have r squared at both 0 and at 8. There's still a d theta, and then this will be, just 64, right? So 0 to 2 pi, integral 0 to 2 pi of 64 d theta, so that's just going to be 64 times 2 pi in the end. Okay, that'll be 128 pi. Now, let's actually, based on this, talk about an interactive question. And let's ask the following. Why was Green's theorem so much more convenient? I mean, in other words, think about it this way. That is, outline what we would have had to do, if we didn't use Green's theorem on this problem. So we're referring to the problem that we just did. Yeah, to this question right here. Let's do one more. Okay, so let's try this. We'll evaluate the integral over the curve C of x to the sine of x power, then plus 2x squared y, all of that dx plus quantity x cubed minus ln of quantity 1 plus y squared, all of that dy, where C is a circle, x squared plus y squared equals 3, oriented counterclockwise. If you'd like, you may wish to just give the problem a try on your own. You may want to pause the video just to see what you'd get, and then unpause and see what my work looks like. Okay, so in writing an answer for this, I am actually just going to go ahead and copy-paste. If you've done your work, this I hope won't bother you so much. Take this and just identify this part right there as being capital P, and this part here as being capital Q to match the notation with the Green's theorem that we have been provided. Yeah, and if we write this as a double integral over a region D, so what's D? In this example, we've got, let's see, there's a circle of radius root 3, and so there's a filled-in disk of radius root 3, and that's capital D. So over the region D, we should have here first the partial derivative of Q with respect to x, because that's what the formula tells us here. That's what the theorem tells us. So we look at this, differentiate with respect to x. First term differentiates to 3x squared. Next term, ln of 1 plus y squared just differentiates to 0 as far as x is concerned. Then we copy the minus sign that's in the Green's theorem formula, and then we need partial derivative of p with respect to y. So looking at that, differentiate with respect to y, the first term differentiates to 0 because there's no y's there. The next term will have 2x squared, and then dA. Okay, so then we could actually clean up the integrand. Well, let's do a couple things at once. So 3x squared minus 2x squared is just going to be x squared. Now, we could be writing an integral that ends in a dx dy or a dy dx, but actually that's too much work because of the shape. Just based on what the shape is, it would be much more natural to do this in polar coordinates. So changing the dA into r dr d theta. Ooh, let's see. Let's just, there's x's here, I didn't think about this. Let's just slow down a step. I'm actually just going to keep this as integral over dx squared dA, and one step later, now let's go ahead and convert this as, okay, the x squared is actually, well, x, remember, is r cosine theta. Okay, then we have that quantity is squared, and then the dA becomes r dr d theta. r should go from 0 to root 3, yeah, because that's root 3 is the radius, and then theta goes from 0 to 2 pi. This integral is actually not that bad. There is a little bit of work to do, but let's not take video time to do all that. In the end, I believe you're going to get 9/4 times pi when doing this. So here's the point overall is when you now that we have this new thing called Green's theorem, in general, what you have to do is this. So you've got to make a choice. You have to choose. So if C is a closed curve, then you have two choices. And it's not guaranteed which one's the easier choice, but you should just pursue both options, right? You should either set up the dt integral and just do it like before you had ever learned Green's theorem, or you could use Green's theorem. And one of these might be easier than the other.